recording. And I'm going to, and we're going to begin with what I call an unquiz. And let's see, I need to share this with you. So we'll do this unquiz with this. This is I'm sharing my applications screen with you. And so I'm asking Joshua if he says he can, then all of you can. Can you see a problem here on the PowerPoint? Joshua.
No, there's no problem.
Okay, so I guess I need to try that again. Okay, so I am sharing my application screen with you again.
I can see
it says my connection is poor now, but we'll see if it works, if I can make it work. Now can you see it?
Yes.
Okay, great. Okay, now what I want you guys to do is, and this is an unquiz, and remember that unquizzes have all the advantages of quizzes in that you learn the kind of questions I might ask, and get a sense of where are you caught up, and things like that. But I'm going to ask you to please solve this system of equations that you see here using elementary row operations. And I think I'm going to give you 10 minutes to do this. Now that might be longer than some of you need. Now I want you to do this though the way you would do it on a high stakes assessment. So that is without having any, using any, you really should just use pencil and paper and work through and solve this for X, Y, and Z. And I say solve using elementary row operations. And when I do this, I'm going to change this to an augmented matrix and work through that. Now, whenever I call time is up at 2:15, what is going to happen is we're going to work through it. You're going to grade your own paper, and that just gives you a sense of where you are. It gives you opportunities to ask questions, and if you got the right answer, it will be congratulations. And if not, there will be other things that we'll do and make sure that you learn. So anyway, everybody, we're spending till 2:15 doing this this problem. Okay, Joshua, can you hear me?
Yes.
Great. Okay. So what I'm going to do is I'm ending this show. We're going to go through a solution. Now, if you got the correct answer, that is great. Congratulations. If not, it's not the end of the world. And again, this was based on some things that we did yesterday. And in order to format a solution for this and to go through this, and I am going to open it for general questions and stuff like that, Les. But let's go through this one now. But what I'm going to do is just to keep things lined up, because we don't have a really good way to write on a chalkboard or anything like that here. So what I'm going to do is I am going to go to, and I'm going to share my application screen with you again, but we're going to go to Excel, and I'm going to ask Joshua in just a moment if he can see Excel. Okay, and Joshua, can you see an Excel screen here?
Yes.
Okay, excellent. Now here's what we're going to do, we're going to march through this with Excel screen. And I'm using Excel not so much for the arithmetic of Excel, but I'm using Excel to keep things lined up. So the first thing I'm going to do is I am going to turn that system that we talked about into some augmented matrices, because I asked you to use elementary row operations to do this. And so I can keep things lined up on Excel, and actually this I think will be a good way to do this. Okay, so we have, this is 2, this is 5, this is 2, and this is minus 38. Okay, so that is what the first row is going to be. The second row is going to be 3. This is going to be minus 2. I'm going to center these things in a moment, but I'm going to get them entered first. And this is 4. And this should be 17. Okay, and so that is good. And the third one is going to be minus 6. And this is going to be 1. This should be minus 7. And this is going to be minus 12. Okay, so we have a 3 by 4 matrix, and I'll just make note of that. This is 3 by 4, and this is an augmented matrix. And I haven't written your first exam yet, but I actually imagine I'm going to ask you a question very similar to this. This is one of the reasons we do unquizzes, because you can say, oh, this is what he would expect us to do. Okay, so this is good, and I'm going to call the first row, row 1, row 2, and row 3 that we will have. Now, here is our goal, okay? We want to change this 3 by 4 matrix into one that looks like this. We want to have a 1 here. And in fact, maybe I'll center these things so we have it centered a little bit more. There, it is now centered. Okay, so we want to get a 1 and a 1 along there. And then we would really like to have a 1 here. So you see, we would like to have some 1s, but we need really one. We're going to work to get 1s there. So that's what we're working to get. But what I'm going to have is that anything underneath these is going to be 0. So you see, this is going to be a 0. This is what we're working toward, and we're going to call this row echelon form. And then, so get 1, 0, 0. But now here we get this is a 0, and I don't care what that is because I can solve it. So that's just whatever it is. I'm calling it yellow right now. And so I get that yellow, and this could be a different number. And there's many colors, so I will call that blue. And here, what I'm going to get is this could be any number, and it can be a different number. So I'm going to call that one, I guess, green. And then I have that. And these are going to be, and I will just call this right-hand side 1, right-hand side 2, and this is right-hand side 3. Now those are numbers too. But we need to do, that should have been a 3. Okay, so, and I'm going to center this too. So that is what we're trying to get. Okay, but we want to use elementary row operations. Okay, so the first elementary row operation that we're going to be is we want to do, and this is going to be called a pivot. So what we want to do is we want to get a 1 here, and eventually we'll get a 0 and a 0 there. And here I want to eliminate this to get a 0, and so on and so forth. So my first step is I want to make this one into a 1. So here is the elementary row operations, and here's how I would like for you to describe those. So what I'm going to do is I'm going to take 1/2, and I guess I will just type. So I'm taking 1/2 row 1. And in fact, I'm going to start calling that R1, becomes the new row 1. And Joshua, you're seeing this okay, yes?
Yes.
Okay, great. And Joshua, I know sometimes I will call on you, but feel free to, if something isn't working, feel free to shout out. Okay, well, 1/2 of the row 1, then, that is going to be 1. Is going to be 2.5. And this is going to be, let's see, it is 1/2, so that is 1 again. And this is -19. Okay, so you see this becomes the new row 1, and that is the first row operation that I do. So I'm going to copy this, and I'm just going to paste it over here like that. And I am going to center it in a minute, but these other rows haven't changed yet. So I'm just copying them, and I'm pasting them here, and you see, and I should center that again. But now the only thing that we have done, is this first row operation, and I was using this as kind of a scratch pad. And this is not a bad way for you to do it on your high stakes assessments too, because I'm looking for the right things here and the right numbers here. Okay, and now what I want to do, and this is what's called pivoting, I want to make that 3 that I'm highlighting, I want to make that a 0. So here is my next step. And so my next step is I'm going to say that -3 times row 1 plus row 3, or excuse me, row 2, I'm sorry, becomes the new row 2. Okay, now, and apparently I did something silly here. We'll see what. I don't want help. I just will do it. Okay, and that was supposed to be just text. So I will say -3 times row 1 plus row 2 becomes the new row 2. And by the way, we talked about a theorem how these elementary row operations do not change the values that work in the system. We didn't prove that, but this is the new row 2. Okay, so let's just do that. Okay, so if I do, and I am going to do some calculations just here. In fact, you would be doing it by hand. I probably will. Let's see. Okay, so this is -3 times that one. Okay, and so that's what I get for that one. But then I'm just going to pull this over 1, 2, 3. And you see, so I get -3, -3, and I should have pulled it over one more. And I get 57. So that's what I get when I do -3 times row 1 plus row 2. And but then I'm going to add row 2 to it. So I'm just going to copy this. I'm going to paste it there. And I'm going to add these two. And you see this becomes the new row 2. So I'm adding these things together. And so I'm adding those together, and that will give me that. And I'll just pull that over. So you see this thing that I have here, and I should have gone one more over. I don't know why it's not going over that far. Okay, so this is my new row 2. So you see row 1 is still this. So I'm copying this. And I'm putting it here. Okay, but this is the new row 2. And I don't want these to be formulas, and I am doing a little fancy Excel stuff, and you don't have to worry about that. But I'm going to copy this, but then I'm going to paste this as a number. And that way I've just got numbers there. And this is the new row 2, so I will put it across there. And those are all the row 2 things. And row 3 didn't change. So I'll go to row 3, and I have this one. So I will copy this, and I'll paste it here. And this is what I have now after 2 steps. Now everybody should see what's coming next. I guess I should. Let's see. All right, so I'm good. I'm just going to center these and center there. Okay, so now they're centered. So that is good. Now I want to get a 0 here. And since I want to get a 0 there, what I'm going to do is this is going to be the row operation that I am doing. It will be right here. And so what I'm going to say is -6. You see, you don't even have to worry about typing all this stuff. I mean, you could just write -6 times row 1 R1 plus row 3 becomes the new row 3. I should have just said R3. Okay, and now I am going to do this. So I will say equals, and this is going to be 6 times this guy to get that. But then I'm going to pull this over 3 more times. And I get those. And then underneath this, I'm just going to put the row 3. Then I'm going to add those together. And I'm adding it together even a little more, not as dramatically using the sum theorem, but I get that. But now pull this across. And this is the new row 3. And I am going to, because I used formulas there, I have to copy that and I have to paste it as numbers. This is kind of a little bit of an Excel nonsense thing that I'm doing. That is the new row 3. So this is row 1, 2, row 3. So I'm going to paste that right there. So that is the new row 3, and row 1 and 2 did not change. Okay, so I'm copying that.
Wasn't the
pasting it
6
here.
supposed to
Yes?
be wasn't the 6 supposed to be negative?
Well, the 6 was negative at the beginning of the problem, but now I come to this step. I'm down here where I'm wiggling the cursor. And by the way, I mean, you might be right. I'm just saying. Okay, so now what I need to do is I want to make that into a 0. And so the way to make that into a 0 is to take 6 times, oh, I should have said 6 times row 1, not -6. I think you're right. I mean, I'm going to change this. This is just going to be 6 times row 1, and I'm just doing that by erasing this. Now, I still am thinking about your comment, okay, but 6 times row 1, but that actually is what I did. I took 6 times row 1, and then I'm adding this to row 3, which did have the -6, 1, -7, -12, and then I added them and I get this. So I think I'm right now. I think it was a typo over here that you were talking about. Are we okay, or am I missing something you're trying to tell me?
No, that was it. I was just confused. But that cleared it.
Okay, this is important to me. You aren't confused now.
Correct. I'm no longer
Great.
confused.
Okay, that's great. Okay, and again, your questions are always welcome, although from time to time I will ask for your questions. Okay, now we have completed what is called a full pivot here, and that is good, okay? But now what we're going to want to do is we're going to want to work. Okay, so and you see I've got the 1 there, I've got 0, 0, so I'm good there. Now the next thing I need to do is, and I don't care what is here because I still can solve the problem, but what I'm going to do is I need to make this one into a 0. And that means, and I really don't even have to make that into a 1. I think I'm going to, just for the sake of the discussion. Okay, but now what I'm going to want to do is I want to turn that 16 into a 0 using an elementary row operation. Okay, but the first thing that I'm going to do is I'm going to say that row 2 times, I'm going to say it a different way. Row 2, well, I will say times 1 over 9.5. And actually, it's 1 times a negative 1.5 becomes the new row 2. Because I'm looking to get a 1 there. Now, I don't care what goes here, but I want to get a 1 there. So what I'm going to do is I'm going to copy row 2. Actually, I'm going to do this first. So what I'm going to do is I'm going to say equals, and this is going to be 1 over, actually, it is going to be minus 1 over 9.5. And then this is times, and I'm timesing this 0 here. Okay, and I know that's 0, but I'm going to do that times the whole row, and I'm just pulling these over here to do the calculation. And so we're getting things that aren't looking like fractions, and those really should be fractions. And so let's see, this is going to be 7. All right, so I'm going to try to change the format of these to be fractions. I was hoping this would be good. Maybe it still will be. More number formats. I'm going to do bigger fractions. So I'm going to do the fractions. I'm going to do as many digits as I can, and we'll see how that works. That works okay. All right, so you see I've turned those all into fractions, so that's I guess good. And this becomes the new row 2. So you see row 1 has not changed. So that is good. This is the new row 2, and I've made these into fractions, which is good, because these will be exact answers. So I will, I'm going to copy that, and then I have to paste that as just numbers, and I did that. So now I can paste it here as numbers, and I need to change that to be the same kind of fraction. So I'm going to copy the format here, and I'm going to paste the format there. That didn't work, apparently. Okay, so I need to go fix this. Hold on. Okay. And why did that say 7 4/5? That rounded it off wrong. Hold on. I may decide that this isn't a good way to do it, but there we go. Okay, so now we have that, and now we come to finally row 3, which has not changed. And we only got one more elimination that we have to do. So I'm copying that and I'm pasting it here. Okay, so I have that. Now what I'm going to do, my last step in this process is let's see, let's center those. Okay, my last step in this process is I want to eliminate that. So what I'm going to do is I'm going to take minus 16 times, so this is negative 16 times row 2 plus row 3 becomes the new row 3. And I could have said, and probably should have said, R3. Okay, so I'm going to do negative 16 times that. So this is going to be equal, this is negative 16 times, see, that is of course going to be 0. And then I'm going to pull all of these others over here. And I'm not sure if I can do that, but I'm changing the formatting. You won't have to worry about all this when you're doing this by hand. I'm going to look at fractions, and I'm going to take the big fractions, and maybe this will work. It did. Okay, so that is negative 16 times row 2 plus row 3. This was row 3 right here. I'm copying that, and I'm pasting it here. And now what we're going to do is add these things. So this is equal to, I'm going to take this guy plus this guy. I'm going to pull these across, and we get that. And I'm going to try to turn these into fractions again. This is kind of a messy numerical thing. Okay, and so more number formats, and we'll go to fractions, and we'll do as many fractions as we can. Okay, and that was good. So this is the new row 3. Okay, so I have row 1 and row 2 are finished. So I'm just copying those. And so we'll paste them down here. So row 1 and row 2 are finished, and row 3 is now this one. Now I have to copy this. And I have to paste it as numbers. And then I will paste it here as numbers. And so that is what I have. Now, what I'm going to do then is I'm going to, so what we've done is we've reduced this, but now we're in a good place to do this. Now, note, and I'm going to, I guess, center these things. Okay, and I'm going to make some notes here, and I'm going to say note that we have made the original matrix into a upper triangular matrix. And we have a name for this. We haven't talked about it yet, but we're going to call this row echelon form. We will talk about this. So you want to do this, and we now can solve this. Okay. Now what I'm going to do is I am writing this down, and then we're going to go through and we're actually going to solve this, because we can solve it once we have something in an upper triangular form. And I could ask you a problem like this doing all this, but I also could ask you a problem where we just have I can give you some part way and ask you to finish it. This is -2 over 19. This is -7 and 15 over 19s. And this is 0, 0, 1. And this is 13 over 19. And this is -1 and 7 over 19. Okay, so now what I'm going to do is I'm going to go now to the blackboard. And Joshua, you make sure we get to the blackboard, but we're actually going to finish this problem now. Okay, so I'm going to go back here. I'm going to stop sharing because I'm going to be sharing something different with you. And I'm sharing the blank blackboard. Okay, now what we have is that last thing is, that's 19, that's 26 over 19. So that last thing, in fact, I guess I will write it using a pencil, and this will be kind of sloppy, but I think I probably have to do it like this. So you see that last row that I have there, that really says that 13 over 19 times z, or x3, I forget which one it was, but times the third variable is equal to, and that is minus 26 over 19. So you see, I can solve that last equation there, and in fact, I know there is a solution to that last equation. So what I'm going to do is, okay, I'm getting text there. So what I need to do to solve this is I need to multiply both sides by 19 over 13. Now, when I do that, the 19s are going to cancel with each other, and I'm going to get z equals -2. Is everybody okay with what I did there? And maybe it's not z, maybe it's x3, because I don't remember what the variable was. Okay, no one's asking questions, so I'm going to say, okay, so that one is good. Now I'm going to erase this one, though. So, but now you see, I know that z is -2. So now what I'm going to do is I'm going to erase all of this, and I'm going to write the next row going up in the XL, and that says that, and again, I'm calling it y. I'm not sure if I called it x2 or y, but that says y -2 over 19 times z, and z was -2. Now that's a -2, that's not a z anymore, is equal to, and I had -7. Okay, so that says that y, when I multiply this, I get 4 over 19. So this is going to be, I'm subtracting 4 over 19 both sides.
Row. I thought the second row was -7 and 15 over it's like an improper, or sorry, mixed number with -7.
Oh, I didn't do all that. You're right. It's not -7. Let me do this calculation really quickly. Okay, so 7 times 19 is probably going to be, let's see, that is going to be 3 and 6. That's 133, right? So that's 133 minus 133 over 19. You were right. So minus 133 over 19. We'll try to do an eraser. And we'll call this minus 133 over 19. And hopefully I can change it back to the pencil. Okay, and so this was, I think you said minus 133. And thank you for following along. That was good.
The fraction was -7 and 15/19, so that would be 148/19.
Yeah, I used 5, and so, okay, so we'll try that yet again. And again, thank you. Okay, so it was 15, so I'm adding 15 to that. So that's going to be, let's see, so 7 times 19 was 133, and then I'm adding 15 to that, so that is 148, I think you said. Okay, so we'll have to mess around with this drawing thing again. This is 148 over 19. Now, what I'm doing is I'm subtracting 4 from that, so that becomes 152 over 19. Let's see. So I'm subtracting. Oh, I'm subtracting 4, so that becomes minus 152 over 19, and 152 over 19. Let's see, 8 times 19. Yes, so that becomes 8. So, okay, so we solved for this, and let me find where I am. Here I am. Okay, so whenever I solve this, I get that y is, okay, so I just will go here. Y then is 8. So now we know that y is 8. So y is equal to 8, and z, in this case, or x sub 3 was equal to minus 2. And so now we only need to figure out what x is. And x is the only unknown that we have. Now, and so that means my first equation then is going to be x plus, then this is 2.5. That is x times 2.5, and y was 8. And then we have z was negative 2, but that was a 1, so that is minus 2. That's a 2, not a z. And this is equal to negative 19. And so what we get is, when we multiply this, we get, let's see, that's going to be 20. So that is going to be 18. So x is, let's see, this is 20 minus 2 is 18. I subtract 18, so x is, let's see, it is positive, so I'm subtracting it. So x is minus 37. Are we good with that? Okay, so you see we solved this by back substitution, but it's important that you realize that what we did is we went through and solved this by back substitution, and then but we made a triangular matrix before we really could determine if we had a solution or not. Okay, so the answer here then is x is minus 37. and y is 8, and z is 2. Now I'm going to pause, and you guys were following along, I think. And so what I'm going to do is I'm going to ask you if there are any questions on this this first example. I'm going to count to 10, Mississippi. This actually was a more important example than you might think. And when we start running through definitions and stuff like that, I think you'll realize that this ends up being an important kind of thing. So I'm counting to 10, Mississippi, and again, your questions are always welcome, but you can ask a question now about this one.
I think the 8 is negative from the y, and then that would make the answer to not be negative 37, but x would be 3. Because the 8 is a negative 8. I'm pretty sure.
The 8 is a negative 8, you say?
Yeah, from
I
the
think
last
that's
slide.
correct.
Okay, so anyway, this is x, y, and z, and so we get x is equal to 15, or x is equal to, excuse me, x is equal to, all right, so y was minus 8, so it was minus 2, minus 8, and the x was, what did you say?
Oh, the x would end up just being 3.
3, okay. All right, so anyway, you're expected to be able to solve this. You won't have to use Blackboard. You won't have to use screens. You won't have access to Excel. But the expectation is that you can solve a problem like this. And understanding elementary row operations is something that we covered last time, so you want to be able to do that. Okay, and I'm going to call this Lecture 2. And Joshua is serving as my deputy. And Jesse Hayes Carver did send you GSG information. So you do have you have GSG information. And I am doing, as my plan today, I'm doing the 75-25. So that means at 3:15-ish, we'll take a break. I am going to ask for your questions, but we're going to leap in where we are. And in fact, I'm going to ask Joshua. Now, Joshua, I'm thinking you were here last time. I think we finished this example that you're seeing now on your screen. And I think we also talked about the graphical representation of that this is 1, 0, minus 1. So do you think this is where we are? I mean, you're comfortable with that?
We still have the Blackboard screen.
Are you sharing?
Let's go and find out what I'm doing. No, probably not. Okay, so we have to share application screen. And when we do application screen, we go to here. And I think this might have been the last slide that I showed you. This was a solution to this problem. So that's where we're going to start in just a moment, okay? But anyway, you learned from the unquiz, at least I hope you did. I'm giving you credit for doing the unquiz. But you may have some questions. So I'm going back all the way to the beginning. I'm going to ask, are there questions? And I'll count to 10, Mississippi, in case people have questions laying out there. Okay, very good. So I'm going to go to that slide then that I was showing you. And we're going to go from there. Okay, so the next slide then, and I am watching the time, we're going to go till about 1/4 and then we're going to take a break. Okay, and I have to hide this so you can see it. The big thing here is the theorem at the bottom of the page. So what we're doing is at the moment, we're interested in row operations on the augmented matrix of a system of linear equations. And what happens is the augmented matrices of two linear systems are row equivalent, which means that you get from one to the other by doing a sequence of elementary row operations, then they have the same solution set, and we talked about that. Okay, so now we're going to move on and talk about existence and uniqueness questions. Okay, now soon we're going to show why a solution set for a system of linear equation either is no solutions, one solution, or infinitely many solutions. I've already told you that, but I haven't proven it. But answers to the following two questions will determine the nature of the solution set for this. Okay, so determine which possibility is true for a particular system. We're going to ask two questions. Is the system consistent? Again, consistent means it has at least one solution, perhaps infinite solution. And the other thing is, if a solution does exist, is it the only one? Saying the only one is another way to say, is it unique? These two questions will appear repeatedly throughout our course in different representations. And so let's look at this with this augmented matrix. Now this is called example 2. So we had example 1 and we had an unquiz, and now we're having example 2. Okay, so what this says is determine if the following system is consistent. Now this has variables of x1, x2, and x3, and you have these, but you have to determine if it's consistent or not. Now, the way to determine if this is consistent is to put it in row echelon form like we talked about. So we're going to get rid of that 5x1, and we're going to really just see what happens when we do that. And if we end up with an upper triangular matrix like we did in the unquiz, that means, oh, there is a solution, and we knew that. We knew there was a solution. We didn't have to figure out what the solution was. We just knew that we could do back substitution to get the solution. But let's determine if this one is consistent. So here we go. Okay, first thing we're going to do is, and this is actually the same system that we used in example 1. So that was, back in the day. But what we did is we put it in this row echelon form, and we saw that, all we know, right, by the time we come to here, we don't really care what the solution is. If the question is this consistent or not? Of course it is, because I know that x3 is -1, and then I could figure out what x2 is and x1 is. So when I put this in upper triangular form, I can glance, or the row echelon form, I can glance at this and I can tell if, in fact, if it does have if it is consistent, and in fact, if there's a unique solution. Let's look at one where it's not unique. This is example 3. So we want to determine if the following system is consistent. Now this looks different. You've got different numbers and everything else. But what we're going to do is we're going to do elementary row operations and see what happens with this one. Okay, so we start doing elementary row operations. Now here was the problem that we had at the outset. And this is the augmented matrix, and we don't have to write all those x1s, x2, x3s anymore. Now, a lot of things that is going on here is just elementary row operations. So this is interchanging some rows. This is some elimination you see here. Now I've got, that. And here, now I have reduced it in what is called equation 7. I have reduced this to a row echelon form because I've got the ones or the non-zero numbers here, and I come down to here. But when we get to here, this tells us something different, and the interpretation of this says that 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 15. That can't happen. So you see, if you get a string of zeros here equal to a non-zero number, that says this is inconsistent, and that means that there is no solution to this. Geometrically, what happens if we do that? These two planes, which are, two of the planes here, intersect in a line, but the third one intersects in a different point. So there's not a unique point of intersection. And so that is an inconsistent system. And the only way we can tell, at least with the theory to date, is to do this row elimination, put it in upper triangular form, and then see. So here we've seen situations where we have no solution. This one, we've seen ones in the unquiz as well as the problem that we did, the example we did last time. Those are all, we had two where there was a unique solution. Here there is no solution. I'm going to pause right here. Does everybody understand if you get zeros along here and then a non-zero number, there's no solution? Okay, so I counted to 5, so that's good. Okay, now it is possible, and in fact, let me go back to that just for a second. It is possible for you to end up with 0, 0, 0, and 0. Now what that means is you have what's called a free variable, and you have an infinite number of solutions, and we'll be talking about that very soon. Okay, so let's look here. One thing is, and unfortunately we're going to be doing proctored tests, so you probably won't have time to do this, but you always could check to see if your answer is correct by substituting in and see if it works in all the equations. So that certainly is a way to substitute in. But here is a numerical note, and we are going to have some numerical notes because you see in our class, most of the matrices that we'll be dealing with, perhaps on LSAs we'll have bigger matrices, but just on a proctored test, I can't give you big matrices. But in the real world, there are big matrices. And in the real world problems, which are really big, systems of linear equations are solved by a computer. And so for a square coefficient matrix, computer programs nearly always use the elimination algorithm that we talked about here. And we'll talk about it again in 1.2. And we modify it slightly for improved accuracy. But the vast majority of linear algebra problems in business and industry are solved using computer programs, and they use floating point arithmetic. So you see numbers are represented by zeros and ones, and so numbers are represented as decimals, and these are integers times powers of 10, and so and there's only so many things, so they're a round off that happens. So arithmetic with such numbers typically is inexact, because the results have to be rounded or truncated to fit into the computer. And round-off error is also introduced when a number such as 1/3 is entered, because its decimal representation will be a bunch of 3's, not an infinite number of 3's. But fortunately, and this is actually very good news, inaccuracies in floating point arithmetic seldom cause problems. The numerical notes in this book will occasionally warn you of issues, and this is a whole field of study called numerical analysis. Okay. Now we're going into a thing, and we're going to be talking about the next sort of unit, is we're going to be talking about row reduction and row echelon forms. Now we've actually been doing this, okay? All right, so we're going to talk about an algorithm, and this is an algorithm for solving these. And so this section refines the method that we talked about into a row reduction algorithm to help us analyze any system of linear equations. And by using the first part of the algorithm, we'll answer the fundamental existence and uniqueness question posed in section 1.1. Now, what they mean by there is when you get it to be an upper triangular matrix, you can tell if there's a solution or not. And in fact, you can tell if there's an infinite number of solutions. Now, this algorithm applies to any matrix, not just augmented matrix. And one of the things that's going to happen is you will reuse this tool over and over again. So this is a skill you do want to put in your toolkit because you're going to be using it later. Okay, so the first part is we talk about, let's take an arbitrary rectangular matrix. That means it's not square. It has a different number of rows and columns, perhaps. And we introduce two important classes of matrices that are called the triangular matrices that we talked about before, And we're also going to talk about a different kind of matrix. We're going to talk about one where there is a non-zero column or a row or a column in a matrix. Means that the row or column contains at least one non-zero entry. A leading entry of a row refers to the leftmost non-zero entry in a non-zero row. Okay, now we will talk about putting things into row echelon form in a rectangular, sometimes it's abbreviated echelon, and echelon means staircase because it kind of looks like it's going down steps if it has the following three properties. Now, I'm not going to ask you to repeat this definition, but you do know what the definition is, because sometimes an algorithm will just tell you, oh, put the matrix in row echelon form. And so that's the first step that you do. So these are the three properties that make something into row echelon form. And so you have to have all three of these. And this is kind of a cumbersome definition. All non-zero rows are above any rows of zeros. That means any rows of all zeros are at the bottom. So you have to reorganize things so that happens. The second defining criteria is that each leading entry of a row is in a column to the right of the leading entry of the row above it. That means you're making it like a stair step. So the leading entry in a row, that's the leading entry up here was the definition. That's the leftmost non-zero thing. You are going stair steps, and that means you're getting it, basically you're getting it into an upper triangular thing. And all entries in a column below a leading entry are zero. So these last two really say it's upper triangular. Now, I'm never going to ask you to tell me this definition, but often the directions in an algorithm will say, okay, first you put it in row echelon form. So you do want to know what this means. If a matrix is in echelon form and it satisfies one additional condition, then it is what is called reduced row echelon form. And that is, and actually it says the following additional conditions, there are two of them. If the leading entry in each non-zero row is 1, and each leading one is the only non-zero entry in its column. So that means that it's not only triangular, but the steps that you're going down have ones everywhere. So that is the definition of row echelon form, and this is called reduced row echelon form. And in your calculators and in a lot of computer programs, they will call this thing down here RREF, and up here they'll say REF, or something like that. And so there are computer programs that do this. We're going to be doing a lot of things by hand, but perhaps on some of the LSAs we will do something with computer programs. Okay. All right. So and the algorithm that we talked about here was usually called Gauss elimination, and Gauss was a European in the 1800s, but Chinese mathematicians 2,000 years before he came up with this had an algorithm like that. If you're getting all ones, sometimes that is called the Gauss-Jordan form because of Jordan, who embellished on Gauss. And so anyway, REF is sometimes called Gauss elimination. REF is sometimes called Gauss-Jordan elimination. Okay. All right, so an echelon matrix or a reduced echelon matrix is one that is an echelon form, reduced echelon form. And so that says that the leading entries form an echelon, that is step-like pattern that moves down and to the right. So you see you got a step-like pattern here, step-like pattern here, moving to the right. So these were triangular matrices, and these are in echelon form. And in fact, this matrix, since those are all ones, is in reduced row echelon form, or RREF. Now, so there's some additional examples talking about that. Now, any non-zero matrix may be row reduced. That is, you can take a matrix and row reduce it, and often that's what you're going to be doing. And what you're going to be doing are those elementary row operations that we talked about. However, but you could end up with different echelon forms because there could be different multipliers in different rows. And you could have done the row operations differently. But the reduced row echelon form that one obtains from a matrix is unique. And so this theorem is proved later, and we'll perhaps talk about it. But this says that each matrix is row equivalent to one and only one reduced row echelon matrix. And often what computers do is they solve things by putting them into reduced row echelon form. Okay, if a matrix is row equivalent to an echelon matrix U, we call U an echelon form or row echelon form of A. If U is in reduced echelon form, we call it the reduced echelon form of A. And here it talks about the RREFs that I talked about. So you see often what we're going to be doing this. And this U, you might say, why in the heck did they use U? They're using U because this is called an upper triangular matrix. The U stands for upper triangular because that's what a reduced echelon form looks like. Later on, and I guarantee you one thing that's going to be on the final exam, and it's also going to be on the midterm I-Stakes exam, is putting a matrix in the form LU, because you can factor a matrix A into L, a lower triangular matrix, times an upper triangular matrix. You might say, well, why would I ever want to do that? Well, when you're doing things with computer programs, what happens is sometimes it is very useful to have it in a different form, and the LU factorization of the matrix is important. So this U thing is going to come back. That's one of the reasons we did a thing. Now, I'm not losing track of what time it is. We're getting close to a break, but a lot of this is definitional stuff. So pivot positions. When row operations on a matrix produce an echelon form, further row operations to obtain the reduced echelon form do not change the position of the leading entries. And so the leading entries are always in the same position. Those are called the pivot positions. And here's the definition of a pivot position. So a pivot position in a matrix A is the location in A that corresponds to a leading one in the reduced row echelon form of A. A pivot column is a column of A that contains a pivot position. Okay, and so what we're going to be doing soon is we're going to be looking, in fact, let's just do a little bit more. And again, I do know what time it is. We're very close to a break, so just hang in there. Okay, so all right, so we're going to this. So here what we're doing is we're saying row reduce this matrix to echelon form and locate the pivot columns. Okay, now we're going to use the same approach as we did before. So we're going to do row reduction. So we do that, and here is what happens. So you see the first pivot element, the way we have to do this is we can't make that into a pivot element because it's 0. So what we have to do in this case is interchange row 1 and 4. Okay, so you take row 4 and move it into the first equation, and you take equation 1 and move it into the last thing. So that's something, but now you have a pivot there. Now, what you could do, once you have a 1 there, you could start eliminating things, and you can change all of those into zeros by using elementary row operations, and then we've done that. But then the next pivot element is going to be this one, because we're going stair steps. And so we want to do a pivot here. And so, you know, you can do the things. And so that's the next pivot column. Okay, so you want to get a 1 there. Let's go to the next page. And that just shows the same thing. But you see, now I make these into zeros just as I did. And now I've completed that pivot. Now I come to this one. I can't use that as a pivot. And the reason I can't use that as a pivot is because it's a 0, so I could change things. But now look what you have already. You have that, okay, well, okay, so then we'll go, we're almost finished with this. So we move this up there, and now we have the zeros. Now, if you look at this, you can say, oh, there is a solution. There's a free variable. So that's what, you know, whatever we want it to be. But this is, but here are your pivots. So you have a pivot at 1, you have a pivot at 2, and you have a pivot at -5. Okay, and so columns 1, 2, and 4 are the pivot columns. Okay, I think we're about ready. In fact, we're going to take a break. I went 1 minute over. I'll give you your full 10-minute break. I'm calling it 3:17, and we'll get back at 27. So 3:27, and remember that the rest of this is a shorter time. So 3:27, we're returning. And let's see, Joshua, you're still hearing me though, right?
Yep.
Okay, you're on break now. Let's go see how much. Oh, God. Okay, the clock says 3:26 here. Joshua, you can hear me?
Yes, I can hear you.
Okay, great. So that means we're going to start, and I need to go back to sort of where we were, and I know where I want to try to get to. So we're going to go till 3:50, which is our normal adjourning time. So I am going to stop sharing, and I guess I need to start sharing again. So I'm going to be sharing my application screen, and we're going to be looking at some PowerPoint slides. Okay, and we talked about pivot positions and things like that. I think we were to this slide actually. And so I will make this bigger and then we'll talk about this. Okay, I guess we're really, so this is what a pivot is. A pivot is a non-zero number in a pivot position that is used as needed to create zeros via row operations. So again, I'm not going to ask you what's the definition of a pivot, but the word pivot will come up in algorithms and things like that. So you want to know about it. So this is the row reduction algorithm. And by the way, this algorithm is not going to surprise you at all. So step one, you begin with the leftmost non-zero column, and this is a pivot column. And so it's at the top. Now when, I need to hide this so you can see it. What's going to happen with, let's see. Okay, so we're starting here. And so the pivot position's at the top. So what we're going to want to do is, that is the pivot column, but we're going to want to have a non-zero number up here. So we're going to have to change rows in order to do that. So what we do is we move the bottom row to the top and we switch it because we're comfortable having zeros down here. So that the first step here in this would be interchange rows if you need to. Okay, then select a non-zero entry in the pivot column, and you see we fixed it so that it was not zero, and we so it was not zero, so we interchanged rows. Then what we're going to do is use row replacement operations to create zeros in all the positions below the pivot. So we work to get, and you can see down here we get 3, 0, 0, and so that's what we do. Now, step 4 is we don't have to worry about the other rows. This is 3, 0, 0, but we move to the next pivot position. So this is where we want to have this. And so this is the pivot, and this is the pivot column. So we're going to work to eliminate this 3. And we can do that by multiplying -3 halves times 2. There's all kinds of ways we could do that. But we work and we eliminate that. And so now we have completed the pivot there. And so now what we have is we have done step 4 in the algorithm. Okay, step 5 says create zeros above each. Now we're really done here because this is the last pivot. So we have a pivot there, and a pivot there. And so we've reached an echelon form of the full matrix. And by the way, once you get here, you can solve it. And that's an important thing. And this will have a unique solution because this has this last variable is equal to 4. And so there is a unique solution. But sometimes we want to get it into a reduced row echelon form. So we perform, it says one more step. Actually, it's several steps. But beginning with the rightmost pivot and working upward, you change the pivots into 1s and you eliminate them. So at the end, you have a 1, so what you have is basically 1, 1, and 1. And so that is called the forward phase of the row reduction, and that's the algorithm. And that produces a unique reduced row echelon form. Okay, and so now we have a numerical note that, let's see, do I really want to talk about that? I'm not going to talk about partial pivoting here. Okay. So the row reduction algorithm leads directly to an explicit direction of the solution set. So for example, here, if I looked at this, I would see that, oh, I have a free variable because 0, 0, 0, 0. So you see, it really doesn't matter what x3 is because that's a free variable, because that's always going to be 0 equals 0. So I can declare x3 to be whatever I want, t, or just say it can be anything I want. You see, this is going to tell you I have an infinite number of solutions. And they're of the form x3 is arbitrary, x2 is going to be 4 minus x3 from this, and x1 is going to be 1 plus 5 times x3. So you have an infinite number of solutions. Now, the variables x1 and x2 that correspond to pivot columns in the matrix are called basic variables, and this is important in linear programming. The other variable, x sub 3, is called a free variable because it can be anything we want it to be. Okay, so whenever a solution, a system is consistent, the solution set can be described explicitly by solving the reduced system of equations. And so you see, you can come up with all the infinite number of solutions here by choosing different choices of x3. So if I take x3 to be 1, for example, I get 1, and I get 3, and I get 6. If I take it to be 0, I get 0 for x3, I get 4, and I get 1. So you see there's different choices here. And so when I put this in the reduced form, I can tell the nature, the number of free variables that we have. Okay, so let's look at this. So find the general solution to the linear system whose augmented matrix has been reduced to this. And by the way, you see we've already reduced it here. So I could, in fact, give you this kind of a problem, and you could say, oh, well, I know the last variable is 7, so you can work through to find what we have for these. And so we can do row reduction, and what we find in this one then is that see, this is 1, 2, 3, 4, 5. There's 5 so I have that this variable is 7. This is also what I'm able to do is do row reduction. So I'm doing row reduction as I go through here. I get it into the upper triangular system. And so I know, since there were 5 variables, because there were 5 columns, I know that this is what I have. So x5 is 7. This is x3 minus x4. x4 is 5. And x1 plus 6x2 plus 3x4 is this. So what we can determine when we work through this, we know what this is. This is the remaining 4 variables, but when we do row reduction, we'll find out that x4 is free and x2 is free. So you can see you can have more than one free variable. Okay, and then you can do back substitution to solve it. Now, I am going to move ahead to the numerical note. And the reason I'm moving ahead to the numerical note is one thing that some students in the Calculus 2 class ask is, well, I'm really unclear about these low stakes assessments. What are they? What do they look like? And things like that. So I gave them one, and I'm going to give you one too, but it has to do with this numerical note. So please pay attention to this this numerical note that I'm going through. In general, the forward phase of row reduction takes much longer than the backwards phase. Now, the backwards phase is when you're doing that back substitution. An algorithm for solving a system is usually measured in flops. Now, flops stands for floating point operations. And I know it's a little bit silly, but they use the FLO here and they use the P here. And so that's how we get flops. Floating point operations, and they use plural. So a flop is one arithmetic operation, plus, minus, times, or divide on any two floating point numbers. Okay, so for an n by n plus 1 matrix, that is n rows and n plus 1 columns, the reduction to echelon form can take 2n cubed over 3 plus n squared over 2 minus 7n over 6 flops. And when you're talking about the order of magnitude of this, the order of this is of order 2n cubed over 3, because that's the highest order thing. Now, this is what people in computer science and in other kinds of science are very interested in algorithms. How long does it take to do? And so this is, the number of operations that it takes. In contrast, further reduction to reduced echelon form needs at most n squared flops. Now, this numerical node is part of LSA 1. And so here is LSA 1. So what I'm asking you to do, and again, please understand that, Joshua, I changed the format. You can still see the PowerPoint slide, right?
Yes, we're currently looking at the PowerPoint.
You're seeing PowerPoint? Yes.
Yes.
Okay, good. Okay, so this LSA1, I'm going to say that this is due. Now, by the way, I'm not trying to induce anxiety with these LSAs, but they're about learning. So I do give you due dates. And I'm going to say due before midnight on Sunday. And I have to figure out what Sunday is. I think Sunday is the 19th. We'll just say it is. So it's 6/19. That might be Juneteenth. I'm not sure. Okay, anyway, so this is going to be due for midnight. Now, I don't mean to cause a crisis with you, though. That means that, you could turn it in at 11:59, and I'm not going to deduct points if you turn it in on 6/20 at 12:15 or something like that. So this is not anxiety, but I do want to have a due date. So what you want to do is you want to prove these numbers. So actually go through and talk about, if you have an n by n plus 1 matrix, that it takes this many floating point operations to reduce to echelon form. And this is the other part, it takes n squared flops to reduce it to reduced echelon form. Now, that's a proof, and you can get help, you can work together, there's a lot of things that you can do, and it's about learning, and it's also about learning the tools. You can meet with Jesse Hayes Carver on this and stuff like that. But what I'm going to do is, in the balance of the period, we have a little over 10 minutes, I'm going to talk a little bit about proofs. And this is the first time I've talked about it, but we're going to have a lot of proofs in this class. So what I want you to prove is this one right here, that these are the formulas, that it's this one and it's that one. And so that's what I'm asking you to prove. Now I'm going to pause just for a moment before I start talking about proofs in general to ask if people have questions about what I'm asking you to do here. And I'll count to 10, Mississippi.
Would you be able to go back to that slide for a quick second?
Is this the one you want to go back to?
Yes, thank you.
Okay. And I am going to post these. Oh, I know another thing I want to say. I do plan to post these things on YouTube, but they're also available within Blackboard Collaborate because I recorded them. And so you can just go to those and you can look at them there. So they're there already. And I am going to post the slides, but I ended up getting involved in some stuff yesterday that I had to deal with, COD stuff actually, so I didn't post it, but these will be posted. So this is here, and you asked me to go back, and are you good with this now?
Yeah, thank you. Yes.
Now, when anybody asks a question, and I think I've answered it, I start my count again, so I'm going from 1 to 10 again. So do people understand what this is about? And it's not about huge anxiety, but it's something serious for you to do.
Apologies, this is a little bit more of a question about the course format. I joined the class late yesterday, so I missed this if you covered this yesterday. But for LSAs, what's the format that we're turning them in?
Okay, that's a fine question. That's probably a question that more than just you have. You should write this up neatly in a legible form. And then what you're going to do, and I haven't done it yet, but Jesse Hayes Carver or I will create a womb for you to upload it into Blackboard. And so what I'm looking for you to do is to do the work, change it into a PDF, and upload the PDF to Blackboard. Now, I'm not sure that answered your question, but that was my first attempt to answer your question. Does that get you there?
Yeah, so when you say written out neatly, then are you expecting a photograph of a handwritten proof, or are you wanting it just like format?
A handwritten proof is fine. You don't have to put it in LaTeX or something like that, although that would be really nice. But a neatly written, handwritten proof can be fine. But it really should be legible.
Yep. Thank you.
Can it be
okay? I'm starting again with my count. Oh, it sounds like I might have another question already. Go ahead.
Can it be written on like a tablet, or does it have to be on paper?
It can be written on a tablet, but then what you probably will do, and I know there's all kinds of software to do this, but what you would do then is you would take a picture of your tablet work, or maybe it's going to be pictures of your tablet work. I will tell you that Microsoft Office Lens is a free app, and it will consolidate multiple pages into a single PDF, which is nice. And so you'll upload it that. So I don't care where you write it, but what's being uploaded, I do want that to be a PDF, and I do want it to be legible and things like that. So and again, it's not like you're developing a photograph for sale or something, but it really does need to be readable.
Okay, so it can be written in any legible format or medium as long as the last version that's uploaded is a PDF.
That's right.
Okay, thank you.
And in fact, it can be a picture that you convert to a PDF.
So then we can use things like Excel to just do our work in?
You could, except this is a proof. Okay, so I guess we're going back here. You see,
right.
This isn't a. I mean, there's calculation, but it's not. I'm trying to think of how to say this. It's not a calculation where the answer is 5. The last line of your proof is, oh, and I add all these things together, and this is what I get. So it's more algebra than it is. It's not so much an Excel thing.
All right, sounds good.
Okay, I'm still counting. Okay, I'm finished counting now. It's 3:45. We have 10 more minutes. So I'm going to start talking a little bit about proofs. Now, maybe some of you guys really are excellent about proofs, but others aren't. Okay, so I'm going to talk a little bit about types of proofs, and we're going to encounter a bunch of proofs in this class, really proving things. And in fact, that LSA1 is a proof. Anyway, so in mathematics, proofs are arguments that convince the audience that something is true beyond all doubt. So it's not just, oh, I think it's true, it's you prove it's true. So a proof is a presentation of logical arguments that explains the truth of a particular statement by starting with things that are assumed to be true and ending with what we are trying to prove. So your last statement in that proof of LSA1 is going to be that equation. Now, there are different kinds of proofs. They're proof by contradictions. There's all kinds of different. We're going to talk about direct proof here. And I know I don't have a lot of time, but that's kind of okay. So I'm going to talk about what is a direct proof. A direct proof is a logical propagation of statements that show truth or falsity of a given argument. And we can reference theorems if we have theorems. We can use definitions and postulates, axioms. And sometimes there are baby theorems that are called lemmas. Okay, in other words, a proof is an argument that convinces someone truly that something is true. So a direct proof begins with an assertion and ends with a statement of what we were trying to prove. Okay, so in this one, we want to show that for an n by n plus 1 matrix, the reduction to echelon form can take this many flops, and that further reduction to reduced echelon form needs at most n squared flops. So that's that's what you need to think through there. And here I'm going to do one proof for you. I may only have time for one proof, but this is a proof of the quadratic formula. Okay, and truly this is a proof. So what we do is we start with, there's two those there, sorry about that. Start with the standard form of a quadratic equation. So that is ax squared plus bx plus c is equal to 0. Now, a does not equal 0, and the reason that a does not equal to 0, because if a were equal to 0, this wouldn't be a quadratic, because that wouldn't be there. It would be a linear equation. Okay, so now we're going to just do algebra. I'm not writing reasons for these, but I'm really doing calculations. So the first thing I do is divide all the way through by a. So I divide all the way through by a, and then I have this, because 0 over a is 0. Okay, and then what I can do is I can subtract this c over a from both sides. It goes away here. So I have x squared plus b over ax is equal to minus c over a. Now then, and sometimes proofs, you have to be really creative, sometimes in proofs. And here, this is called completing the square, and maybe you studied it, but if you didn't, you kind of say, where the hell did that come from? But here we add the same thing to both sides. So we're adding b over 2a whole squared to both sides. We certainly can do that. And then I recognize that this thing really could be factored as x plus b over 2a whole squared. And then over here, I get a common denominator, which is 4a squared. So I get this, and I can reorganize this. So I can have x plus b over 2a whole squared is equal to, and this is b squared minus 4ac all over 4a squared. And then I'm going to take the square root of both sides, which is the next thing. And so I take the square root of both sides, and then I subtract b over 2a from both sides. And here, this should be plus slash minus. And so you can solve for x then. You've solved for x by adding this minus b over 2a. So x is equal to minus b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And that is the quadratic formula. So you see, what we've done is we really proved the quadratic formula by going through all of that. And so that's an example of a direct proof. And I pretty much run out of time, but we'll pick this up tomorrow, and we'll talk maybe a little bit more about proofs, then we'll go do some other things. Okay, time is precious. Each day must count. Do the math. It will make you strong. See you guys tomorrow. Bye-bye. And thanks, Joshua.
I just have a quick question about the homework.
Oh, I'm sorry. I didn't realize you were here. By the way, I'm going to turn off the recording. I'm glad you were there.